Hello friends, welcome to UGC EPG Pathshala. Myself Swati Katyar, Senior Research Fellow, Birla Institute of Scientific Research, Jaipur. Today in this video, we will discuss about the supervised classification. We will start with the introduction. The purpose of the image classification is to categorize all pixels in a digital image into different land use land cover classes. Depending on the interaction between the computer and the interpreter during classification process, there are two types of classification. These two main categories used to achieve classified output and are called supervised classification and unsupervised classification techniques. Out of the two major methods of the image classification, supervised classification is generally chosen when analysts have good knowledge of the area. In supervised classification, analysts select representative sample for each land cover class. The software then uses these training sites and applies them to the entire image. Supervised classification uses the spectral signature defined in the training set. There are many classification algorithms used in the supervised classification, such as maximum likelihood and a minimum distance classification. Supervised classification is based on the idea that a user can select sample pixels in an image that are representative of the specific classes and then direct the image processing software to use these training sites as references for the classification for all other pixels in image. Training sites are selected based on the knowledge of the user. The user also sets the bound for how similar other pixels must be to group them together. These bounds are often set based on the spectral characteristic of the training area plus or minus a certain increment. The user also designates the number of classes that the image is classified into. Many analysts use a combination of supervised and unsupervised classification process to develop final output and analysis classified maps. The schematic of these steps used in the supervised classification is shown in the figure number 1. Now we will discuss about the elements of the supervised classification, that is training data, feature selection, selection of appropriate classification algorithm, post classification smoothing and accuracy assessment. The very first, training data. Training data fields are areas of known identity delineated on the digital image, usually by specifying the corner points of a rectangular or polygonal area using line and column numbers within the coordinate system of the digital image. The analyst must of course know the correct class for each area. Usually the analyst begins by assembling maps and aerial photographs of the area to be classified. Specific training areas are identified for each information category following the key characteristic of a training area. The objective is to identify a set of pixels that accurately represents spectral variation present within each information region. Key characteristic of training areas are shape. Shapes of training areas are not important provided that the shape does not prohibit accurate delineating and positioning of the outlines of a region on digital images. Usually it is the easiest to define rectangular or polygonal areas. As such, shapes minimize the number of vertices and must be specified. The second is location. Location is important as each information category should be represented by several training areas positioned throughout the image. The training areas must be positioned in location that favor accurate and convenient transfer of the outlines from maps and aerial photographs to digital image. As the training area are to represent variation within the image, they must not be clustered in a favored region of the image, which may not typically typify condition encountered throughout the image as a whole. The third is the number. The optimal number of training area depends on the number of categories to be mapped, their diversity, and the resources that can be devoted to delineating training areas. Each information category or each spectral subclass should be represented by a number of training areas to ensure that spectral properties of each category are represented. The next is placement. Training area should be placed in image in a manner that permits convenient and accurate location with respect to distinctive features such as water or boundary between distinctive features on image. They should be distributed throughout the image so that they provide the basis for representation of diversity present within the scene. The next is uniformity. Perhaps the most important property of a good training area is its uniformity, homogeneity. Data within each training area should exhibit a unimodal frequency distribution for each spectral band to be used. Now evaluating signatures. There are tests to perform that can help determine whether the signature data are a true representation of a pixel to be in a classified for each class. One can evaluate signatures that were created either from unsupervised or supervised training. These are number of methods for evaluation of the signatures. The first is graphical, then signature separability, then divergence, then transform diversion. Now we will discuss about the graphical method. In graphical method, the basic is draw and view ellipse diagrams and scatter plots of data file values for every pair of bands. In signature separability, it is a statistical measure of a distance between two signatures. Separability can be calculated for any combination of bands that are used in a classification. This method can calculate Euclidean distance as given in the equation. Now divergence. Divergence is calculated by the equation as shown, where I and J are the two signatures being compared. Ci is the covariance matrix. Mu I is the mean vector of signature I, Tr is a trace function, and T is a transportation function. Now transform divergence. As shown in the given equation, this is an improved method of the evaluation of signature, where I and J are the two signatures being compared. Ci is again the covariance matrix, mu I is the mean vector, Tr is the trace function, T is a transposition function. The scale of the divergence values can range from 0 to 2000. As a general rule, if the result is greater than 1900, then the classes can be separated. Between 1700 and 1900, the separation is fairly good. Below 1700, the separation is poor. Selection of appropriate classification algorithm. Various supervised classification algorithm may be used to assign an unknown pixel to one of a number of classes. The choice of a particular classifier or decision rules depends on the nature of the input data and the desired output. Parametric classification algorithm assumes that the observed measurement xc for each class in each spectral band during the training phase of the supervised classification are Gaussian in nature, that is, they are normally distributed. Non-parametric classification algorithm makes no such assumptions. Among the most frequently used classification algorithms are the parallelepiped minimum distance and the maximum likelihood decision rules. As example of the data samples is given in the figure number 2. Now we will discuss about the parallelepiped classification algorithm. This is the widely used decision rule based on simple Boolean and or logic. Training data in n spectral bands are used in performing the classification. Brightness values from each pixel of a multispectral imagery are used to produce an n-dimensional mean vector, where MC calculates is to mu C1, mu C2, mu C3 up till mu Cn, with MCK being the mean value of the training data obtained for class C in band K out of m possible classes. SCK is the standard deviation of the training data of class C and band K out of m possible classes. Using a 1 standard deviation threshold, a parallelepiped algorithm decides brightness value of ijk is in class C, and if and only if mu ck minus sck is less than or equal to the brightness value of ith row jth column in kth band less than or equal to mu ck plus sck, where C equates is to 1, 2, 3 up till m number of classes, k is the band, the number of band. Therefore, if the low and high decision boundaries are defined as the condition stated in the equation, which states LCK is equal to mu CK minus SCK and HCK is equals to mu CK plus SCK, and the parallelepiped algorithm becomes like the another equation as shown in the equation, LCK less than or equal to BCIK less than or equal to HCK. These decision boundaries from an n-dimensional parallelepiped in a feature space, if the pixel values lies above the lower threshold and below the high threshold of all n bands evaluated, it is assigned to an unclassified category. Although it is only possible to analyze visually up to 3 dimensions, but it is possible to create an n-dimensional parallelepiped for classification process. The parallelepiped algorithm is a computationally efficient method of classifying remote sensor data. Unfortunately, because of some parallelepiped overlap, it is possible that an unknown candidate pixel might satisfy the criteria of more than one class. In such cases, it is usually assigned to the first class for which it meets all criteria. A more elegant solution is to take this pixel that can be assigned to more than one class and uses a minimum distance to mean decision rules to assign it to just one class. Below, figure number 3 shows parallelepiped algorithm. Now we will discuss about the minimum distance to mean classification algorithm. This decision rule is computationally simple and commonly used. When used properly, it can result in classification accuracy comparable to other more computational intensive algorithms, such as the maximum likelihood algorithm. Like the parallelepiped algorithm, it requires that the user provide the mean vectors for each class in each band MCK for training data. To perform a minimum distance classification, a programmer must calculate distance to each mean vector MCK from an unknown pixel. It is possible to calculate this distance using Euclidean distance based on the Pythagoras theorem shown in figure number 4. The computation of the Euclidean distance from point to mean of class 1 measured in the band relies on the given equation, that is distance equal to square root of the BVIJK minus MCK, the 2, and then BVIJL minus MCL into 2, where MCK and MCL represent the mean vectors for class C measured in K and I. Many minimum distance algorithm analysts specify a distance or a threshold from the class means beyond which a pixel will not assign to category even though it is nearest to the mean of that category. When more than 2 bands are evaluated in a classification, it is possible to extend the logic of computing the difference between just 2 points in space using the given equation as shown. Maximum likelihood classification, that is shown in the figure number 5. The maximum likelihood classification decision rule assigns each pixel having pattern measurements or feature X to class C whose units are most probable or likely to have given rise to feature vector X. It assumes that the training data statistics for each class in each band C are normally distributed, that is Gaussian. In other words, training data with bi or tri-model histograms in a single band are not ideal. In such cases, the individual modes probably represent the individual classes that should be trained upon individually and labeled as separate classes. This would then produce unimodal Gaussian training class statistics that would fulfill the normal distribution requirement. Maximum likelihood classification make use of the statistics including the mean measurement vector, divergence, the standard deviation and a probability. Mean of class C for each class and the covariance matrix of class C for band K through I. The decision rules apply to the unknown measurement vector X is decided as per the given equation. Decide X is in the class C if and only if the particular equation specifies, then det Vc is the determinant of the covariance matrix Vc. Therefore, to classify the measurement vector X of an unknown pixel into a class, the maximum likelihood decision rule computes the value PC for each class, then it assigns the pixel to the class that has the largest value. Now let us consider the computations required. In the first pass, P1 is computed with the V1 and M1 being the covariance matrix and the mean vectors for the class 1. Next, P2 is computed using V2 and M2, the continues for all M classes. The pixel or the measurement vector X is assigned to the class that produces the largest or the maximum PC. The measurement vector X used in each step of the calculation consists of n elements. For example, if all the 6 bands were being analyzed, each unknown pixel would have a measurement vector X of a brightness value of a pixel at location I and j in band 1, 2, 3, 4, 5, 6 and so on. The base decision rule is identical to the maximum likelihood decision rule, that is, does not assume that each class has equal probabilities. As shown in the figure number 6, a priori probabilities have been used successfully as a way of incorporating the effects of a relief and other terrain characteristics in improving classification accuracy. The maximum likelihood and base classification require many more computation per pixel than either the parallelepiped or the minimum distance classification algorithm. They do not always produce superior results. Now, classification accuracy assessment. Quantitatively assessing classification accuracy requires the collection of some in situ data or a priori knowledge about some part of the terrain which can be compared within the remote sensing derived classification map. Thus, to assess classification accuracy, it is necessary to compare the two classification maps, the first the remote sensing derived maps and the second the assumed true map. The assumed true map may be derived from in situ investigation or quite often from the interpretation of remotely sensed data obtained at a larger scale or a higher resolution. Now, overall classification map accuracy assessment. To determine the overall accuracy of a remotely sensed classified map, it is necessary to ascertain whether the map meets or exceeds some predetermined classification accuracy criteria. Overall accuracy assessment evaluates the agreement between the two maps in total area or each category. They usually do not evaluate construction error that occur in the various categories. Now, site-specific classification map accuracy assessment. This type of error analysis compares the accuracy of the remote sensing derived classification map pixel by pixel with the assumed true land use map. First, it is possible to conduct a site-specific error evaluation based on the training pixel used to train the classifier in a supervised classification. This simply means that those pixel location ij used to train the classifier are carefully evaluated on both the classified map from remote sensing data products and assumed to be a true map. If training samples are distributed randomly throughout the study area, this evaluation may consider representative of the study area. If they act biased by the analyst, a prior information of where certain land cover types exist in the scene. Because of this bias, the classification accuracy for pixels found within the training sites are generally higher than for the remainder of the map, because these are the data location that were used to train the classifier. Conversely, if other test locations in the study area are identified and correctly labeled prior to classification, and if these are not used in the training of the classification algorithm, they can be used to evaluate the accuracy of the classified map. This procedure generally yields a more credible classification accuracy assessment. However, additional ground truth is required for those test sites, coupled with the problem of determining how many pixels are necessary in each test site class. Also, the member of identifying the location of the test sites prior to classification is important, since many statistical tests require that location can be randomly selected so that the analyst does not bias their selection. Once the criteria for objectively identifying the location of a specific pixels to be compared is determined, it is necessary to identify the pixel assigned to each pixel in both the remote sensing derived and the assumed true map. These data are tabulated and reported in a contingency table, that is the error matrix, where overall classification, accuracy and misclassification between categories are identified. It takes the form of an M cross M matrix, where M is the number of classes under investigation. The rows in the matrix represent the assumed true classes, while the columns are associated with the remote sensing derived land use. The entries of the contingency table represent the row number of a pixel encountered in each condition. However, they may be expressed as percentages if these number becomes too large. One of the most important characteristics of such matrices is their ability to summarize error of omission and commission. These procedures allow quantitative evaluation of the classification accuracy. Their proper use enhances the credibility of remote sensing derived land use information. Now, classification error matrix. One of the most common means of expressing classification accuracy is the preparation of the classification error matrix, sometimes called confusion or contingency table. Error matrix compare on a category by category basis the relationship between known reference data and the corresponding results of an automated classification. Such matrices are square with the number of rows and columns equal to the number of categories whose classification accuracy is being assessed. Figure number 7 is an error matrix that an image analyst has prepared to determine how well a classification has categorized a representative subset of pixels used in the training process of a supervised classification. This matrix stems from classifying the sample training set pixels and listing the known cover types used for training versus the pixel actually classified to each land cover category by a classifier as shown in the table. Now from this table we can calculate the overall accuracy, the user's accuracy and the producer accuracy. By applying the formulas, we can say the producer accuracy for water is 100%, for sand it is 16%, for forest it is 88%, urban it is 51%, corn it is 85% and hay it is 82%. Whereas the user's accuracy when calculated for water comes out to be 99%, for sand it is 72%, for forest it is calculated as 87%, for urban it is calculated as 99%, for corn it is 74% and for hay it is 75%. Now overall accuracy when we add all the data, that is 480, 52, 313, 126, 342, 359 divided by 1992, it comes out to be 84%. An error matrix expresses several characteristics about classification performance. For example, one can study the various classification error of omission, that is exclusion, and commission, that is inclusion. Note, in figure number 7, the training set pixels that are classified in the proper land cover categories are located along the major diagonal of the error matrix running from upper left to the lower right. All non-diagonal elements of the matrix represent error of omission or commission. Omission errors correspond to 9 diagonal elements. Example, 16 pixels that would have classified as sand were omitted from that category. Commission errors are represented by non-diagonal row elements. Example, 38 urban pixels plus 79 hay pixels were improperly included in the corn category. Several other measurements, for example, the overall accuracy of classification can be computed from the error matrix. It is determined by dividing the total number correctly classified pixels by the total number of reference pixels. Likewise, the accuracy of the individual categories can be calculated by dividing the number of correctly classified pixels in each category by either the total number of pixels in corresponding rows or columns. Producer's accuracy, which indicates how well the training set pixels of a given cover type are classified, can be determined by dividing the number of correctly classified pixels in each category by the number of training sets used for that category, which is the calculation of column in total. Whereas the user's accuracy is computed by dividing the number of correctly classified pixels in each category by the total number of pixels that were classified in that category, that is of a row total. Now this figure is a measure of commission error and indicates the probability that a pixel classified in a given category accurately represent the category on the ground. Note is that the error matrix in the table indicates an overall accuracy of 84%. However, producer accuracy range from 51%, that is of urban, to 100% of water, and user's accuracy range from 72%, that is of sand, to 99%, that is of water. This error matrix is based on training data. If the results are good, it indicates that the training samples are spectrally separable and the classification works well in the training areas. This aids in the process but indicates little about classifier performance elsewhere in the scene. Now we will discuss about the Kappa coefficient in very short. Discrete multivariate techniques have been used to statistically evaluate the accuracy of a remote sensing derived maps and error matrices since 1983 and are widely adopted. These techniques are appropriate as the remotely sensed data are discrete rather than the continuous and are binomially or multimonially distributed rather than the normally distributed. Kappa analysis yields a Khath statistics. Khath is a measure of agreement of accuracy. A Khath statistics is computed and stated in the below equation, whose extension states R is the number of rows in the matrix, xii is the number of observation in a row I and column I, and xi plus the marginal total for the row and I column respectively, and n is the total number of observation. Hope you have enjoyed this lecture. Thank you.